All right, good morning. Welcome back to Elements of Calculus 2. Today we are talking about something called Taylor polynomials, and this is a way of taking kinds of functions that are a little bit problematic and turning them into polynomials. And if you remember from Calculus 1, doing any kind of calculus with polynomials was so much easier than pretty much anything else you could possibly think of. And this happens, we have like numerically difficult functions to work with or anything like that. We're going to go ahead and take these things and turn them into polynomials. And the idea of a Taylor polynomial, we'll call this tx, is that's going to be the zeroth derivative of x at zero. So I'll just go ahead and replace that with a zero times x to the zero over 0 factorial. 0 factorial is equal to 1 because, okay? And then we're going to add to it the first derivative at zero. So the original function at zero plus f prime of zero. So we're trying to get the slope in there. And we've taken the first derivative. So we're going to divide by 1 factorial. 1 factorial just is equal to 1 times 1. So that's just going to be 1. Plus, and then we have f double prime at zero. Okay, this times x, by the way, times x squared over 2 factorial. 2 factorial is equal to 2 times 1. Okay, plus f triple prime, okay, of 0 times x3 over 3 factorial. Okay, 3 factorial is equal to 3 times 2 times 1, which in this case would be 6. Okay, plus, and we'll say this is f4. Sometimes they use Roman numerals, but f4, the fourth derivative, x to the fourth over 4 factorial. 4 factorial is 4 times 3 times 2 times 1, which is equal to 12 times 2, which is 24. So what's happening here is the powers are going up, but the weight of that power is going down by a factorial. So the whole thing is we're trying to balance out that we're trying to get better ideas of the slope, right, with our derivatives, multiply them by a weighted polynomial at, the value of the power of x, and then we're trying to divide that by the fact that when you take these derivatives, we're going to have a 3 times 2 times 1 kind of an idea here. So that's the idea for these things. If you ever want to sound like the smartest person in the room, the way to do that is you should ask somebody if you could approximate the solution with a series. That will almost always go over like, wow, that's a brilliant idea. What did you think of that? And I'll tell you where you thought of that, because that's exactly what happened to me, because we were trying to figure out we had to figure out the length of a satellite. So we have our satellite sitting on Earth. My eyeball is a satellite. And we could pretty much run a laser up to the beginning of it and run a laser to the middle, the end of it. And then what we had to do was figure out the length of this whole thing. Well, the equation we had, somebody had the brilliant idea that we were going to measure satellite, or we are going to measure laser propagation in the atmosphere in centimeters. Now, I don't remember exactly what the geosynchronous orbit is for satellite, but it is a couple of few thousand kilometers. Okay, so you have to say this is going to be, I think it's like 10,000 kilometers, so 10 times 10 to the negative 3. So 10,000 that's 10,000 meters, right? No, that's 10,000. So I want to go 10,000 km. And then we're going to go ahead and convert this to centimeters. So that's what our value was. And we had to figure out like what the actual height was over here in order to figure out the length of the satellite. And the computer is just, there wasn't enough numbers in the computer. We kept getting 0 for the length every time because this was never going to work out. And our senior scientist was like, hey, could we approximate that with a series? I'm like, absolutely, let's try that. And that's how we pretty much got this thing to work. So I just pretty much solved for the length of the actual height, or the height here, doing some triangle stuff, figured that out, approximated it with a series, and did that. The whole point was that there wasn't any minuses in my series. It was just pluses. So we could go ahead and approximate the length without having to worry about like a big number minus big number and get close to 0 for the computer to not have a good time with. But all that said and done, that was very interesting. So the reason you want to use this is because for sometimes numerically sensitive type of things where you have things that are close to zero, or you're close to dividing by zero, or maybe you have a logarithm that has something close to one in it, which means you're going to get zero, or worse, you get a logarithm close to zero, which means you're going to get negative infinity. So it avoids having to do that because it turns all of these problems that might be a little bit problematic numerically into things that are polynomials, and polynomials are very easy. They're very stable for almost all the numbers we're going to use. So that's why you want to be able to do this. The first problem we're going to do is not one that we would ever have to ever worry about because it's the square root of x plus 16. And we usually expand around x equals 0. Okay, so that's where this is going to go with, and that's a Taylor polynomial. There is a very closely related friend called a Maclaurin polynomial, which is x equals some other value. Okay, now we don't spend a lot of time doing x equals other values for the Maclaurin polynomials. We almost always just worry about the Taylor polynomial. Your book pretty much does Taylor polynomials, so that's where I'm going to spend most of our time. Okay, other than that, we're just going to say, okay, this is x minus a instead of x equals 0. Okay, so if you ever have to use this outside, we would go ahead and just replace, instead of x equals 0, we replace x equals 0 with x minus a. A is the value you want to keep this around. But these are classroom exercises. We're trying to keep things simple here, and you're going to see that I'm going to fail on that statement. So what we're going to do here is we have to take a whole bunch of derivatives. So the first thing I'm going to do is I'm going to write this in terms of a calculus problem because I don't want to take a square root. I don't want to take a derivative of the square root of something, but taking the derivative of x plus 16 raised to the 1/2, that's an easy derivative. So our first value here, we don't take a derivative. We just say, okay, this is just f of x or f of 0, f0, the 0th derivative. This is just going to be my x plus 16 raised to the 1/2 power. My first derivative, okay, and this is just going to go back to what you learned in Elements of Calculus 1. We pull the exponent down, so we have 1/2 x plus 16, subtract 1 from the exponent, so 1/2 minus 1 is going to be negative 1/2, and we're just going to create a whole bunch of derivatives here, okay, and since I've got to make a fourth degree polynomial, we're going to take 4 derivatives. So we're going to go ahead and deal with this. This is negative 1/4, 1/2 times a half. We pull down the 1/2 in front, so we end up with an x plus 16, and then we go ahead and subtract 1. So 1/2 minus 1, we get negative 3/2. F triple prime, so the third derivative of x is equal to, and we'll go ahead and do this. So this is going to be a positive, negative times negative is positive, positive 3/8 x plus 16 raised to the negative 5/2. And then finally, F4, a lot of times these are written with Roman numerals. When we get to be bigger ones, I guess it can't be too big, but equal to that. And then we end up with 3 times 5. So I'm taking a derivative. So this is coming down in front. So we have 3 times 5, which is 15. And then 8 times 2 is negative 6, or 16 rather. We have a negative value here. X plus 16 raised to the negative 7/2. Okay, so that's our first sort of chore when we have to go ahead and sort out Taylor polynomials. Okay, the next thing I want to do, I'm just trying to lay this out so it's a nice and neat kind of a thing because it's real easy to start losing track of everything when you're trying to do this. Okay, the next column of my table is I'm going to go ahead and insert my x equals 0 into this thing. And we're going to go ahead and figure this thing out numerically. So I'll put a very mini kind of a column in here where this is just going to be 16 to the 1/2 power, 1/2 times 16 to the negative 1/2 power, negative 1/4 times 16 to the negative 3/2 power, okay, 3/8 times 16 to the negative 5/2 power, and of course, negative 15/16 raised to the 16 to the negative 7/2 power. Okay, and we're just going to go through and deal with each of these little pieces here. So I'm going to go ahead and put another little bar here. Okay, I'm going to run out of room because this is not a very big idea for a bar. Okay, but we'll go ahead and we'll just evaluate these little pieces here. Okay, so you definitely want to like use like a landscape view of this thing in order to figure this out. So this is just going to be 16 to the 1/2 power. We get 4. Okay, great. We have 1/2 times 16 to or 1/2 times 16 to the negative 1/2 power. 16 to the 1/2 negative 1/2 power is going to be 1 over 4. So this is just going to be 1/2 times 1/4. Okay. And then the next little piece here. So we're going to say, okay, that's 4. And then we have 8. And then we'll go ahead and say this is going to be what? Negative, okay, negative 1/4. Okay. Now I plugged 16 to the negative 3/2 into my handy calculator and end up with 1 over 64 sitting there. The negative sign, remember, means 1 over. Okay. So we can go ahead and do that. And then I've got 3/8. Actually, I'll go ahead and do that for us right now. Okay. Let me see if I can find my calculator for us. Okay, so let's go ahead and do that. Okay, it's my fancy calculator because that's what I have for the computer here. But when I did this on paper, I just used my like 4-function calculator kind of an idea. It wasn't that big. Okay, so we're not going to do any of the operations that are going to require a graphing calculator for this. So the fact that you can't use this fancy calculator is not going to impact what's going on here. So I'm going to keep in the fact that the negative means it's going to be on the bottom. So I'm just going to go ahead and type in, I've got 16 caret to the 5/2. Okay. And it's like, what about it says it's negative? I'll put it under a 1 in just a moment, but this is easier to see for what's going on here. So it's 1 over 1024 here. Okay, so these numbers are going to get kind of awful kind of quickly. Okay, so here we have negative 15 over 16 times, and now I've got to do 16 to the negative 7/2. So we're going to say 16 caret, and then we're just going to put a parentheses here. We're going to say negative, or we're just going to say, I'm not going to worry about the negative. I'll do that in my head. 7 divided by 2. Okay, so it's the square root of 16 raised to the 7th power. Okay, so we got, see, this is going to be an awful number. So this is 1 over, because remember the negative sign wasn't in there. So we have 1 over, and this is 16384. 16384. Okay, so we're almost there. I'm just going to start putting this stuff together. So this is going to be 4, and then it's x to the 0. So 4 times 1. And then this term is positive, so we're going to get 1/8 raised to the x over 1 factorial. Okay, this is over 0 factorial. We're going to get 4 times 64, so let's go ahead and have a look at that. So it's going to be 4 times 64. Okay, so that was negative 1 over 256. And this is my second derivative. So this is going to be x squared over 2 factorial. Okay, so then we're going to have 3 over 8 times 1024. So I'm just going to go ahead and say 8 times 1024. All right, so that was 8192. So we have 3 over 8192. That's 8 times 1024 times x cubed over 3 factorial. Okay, and we're almost there. Okay, so we have a negative 15 over, we're going to do 16 times, there we go, 16 times 16384, 16384. So you can see that the most important thing on here is just kind of organizing what has to happen. So I ended up with, yeah, 16 times 16384. So we end up with 262144. 262144 x to the 4th over 4 factorial. Okay, almost done. One more step. Okay, and I'm just kind of dragging this out more than anything else. I mean, you could do this step, you could do all these steps faster, but my end solution here, when I actually write down my answer, my Taylor polynomial is going to be, and I've got 4, because 4 divided by 1 is just going to be 4. So I've got 4 plus, and then we have, what's our next value? It's 1/8 x. Okay, so we have 1 over 8 x over the 1 factorial. Okay. And now I'm going to say, okay, what's 256 times 2? Okay. So we have 256 times 2, 2 factorials, 2 times 1. Okay. And that was 512. So we're going to say minus 512, 1 over 512 x squared. Okay. And now we're going to say plus. And now I want 3 over 8192 times 3 factorial. So we're just going to take 8192, okay, times, not divide, times 3 factorial, which is 6. So 8192 times 6. The 3's will actually cancel, but I'm not going to worry about that right now. I'm going to say, okay, let's see if we can't just get an answer without worrying about trying to reduce fractions. So we have 3 over, this is 49, 152. So 3 over 49, 152 x cubed. Okay, and then finally minus 15. And I'm going to say, okay, what is 262? 262, 144 times 24. Okay, because 24, not 25, 24. Because 4 factorial is just 24. Again, a 3's we're going to cancel out, a 2 will cancel out. So some stuff will cancel with this. This won't be exactly like nice and neat in the most reduced form, but we're going to go ahead and say 262 times 144, and I ended up with 629. Okay, what was this? This was 629, um, 629, 1456. 456. 1456 x to the fourth power. Okay, and this would be my Taylor polynomial for a fourth degree Taylor polynomial. I guess we could keep going, but I don't think I really want to. You don't really want to either. But that would be a fourth degree Taylor polynomial for the function, the square root of x plus 16. And again, the reason you want to use this is that negative 16 is certainly far enough away from 0 that we wouldn't feel too comfortable with this. But a lot of times, these values are going to be close to giving you an imaginary number or a 0 where you don't want a 0. So that's why you would want to use this thing, is it kind of sidesteps a numerically unpleasant situation because it turns back into a polynomial. Polynomials are very easy to work with. Okay, so I'm going to go ahead and go back up to here. I did type this thing out in the Desmos. Okay, the red value is the x plus 16, and the blue line is the polynomial that I just came up with. And it's an x to the fourth polynomial. You can see the x to the fourth polynomial is an even polynomial with a negative leading coefficient. So the end behavior of this thing looks correct. But as far as we get are kind of close to 0 and all the way out to 20, right, is pretty close to 0. So even out to like negative 16 over here, this is a pretty reasonably good approximation, although it gets worse and worse and worse the further away you go. Okay, so you can see like it's not perfect forever and ever and ever. It can't be. But the more terms you have, the closer it's going to be. So with that, I will say thank you very much for watching the video and good luck doing homework, and try not to get intimidated by the fact that the numbers are going to get kind of big. They are. So thank you very much for watching. All right, goodbye.